You want to see a video I made in 2014 before Instagram Reels were even a thing?
I'm going as fast as I can.
So this is me swimming in the Credit River. Credit River runs in Mississauga, pretty close to where my mother-in-law lives. And it runs towards Lake Ontario. It goes to the south direction. Well, I'm swimming north in this video, and as fast as I can, it's probably about 1 meter per second. So I'm swimming relative to the water in the river, north at 1 meter per second. But the water in the river is moving relative to the shore at 1 meter per second towards the south. So if you want to find out how fast I'm going relative to the shore, you add my velocity relative to the water, which is 1 meter per second to the north, plus the velocity of the water relative to the shore, 1 meter per second to the south, and you get 0. I'm not going anywhere. So this is all about one-dimensional motion, which is the topic of today's chapter. So it starts at PDF page 55. There's an kestrel flying through the air. So basically kinematics means how things move, as opposed to dynamics, which is sort of why things move. And by one-dimensional motion, we're just talking about motion along a straight line, meaning that it doesn't turn. So it turns out you can move along a straight line or a curvy line. And these are two very different things in physics. So we're going to start with moving along a line and no turning. And then for two-dimensional motion in the next chapter, we'll talk about what happens when you're actually turning, two or three-dimensional motion. Definitions to go through. Position. So if you have, for example, a coordinate system with an x-axis and an origin, then your position on the x-axis is a number, which could be positive or negative, depending if you're one side of the origin or the opposite side of the origin. So that's position. Displacement means the change in position. Typically, it's going to happen over some time. And the equation here that's important is delta x equals xf minus x0. So xf and x0, those are the final and initial positions. So these little subscripts refer to final, and 0 just refers to initial. It means like the zero time position. So final minus initial gives you this triangle is called delta, so it means the change in x, delta x. That's displacement. So for example, if someone starts at 1.5 meters and goes to 3.5, the displacement is 3.5 minus 1.5 is plus 2 meters. If somebody along their x-axis starts at 6 meters, but then travels backwards to 2 meters, then the final is actually less than the initial. You get 2 minus 6, you get negative 4 is your displacement in that case. So distance is the okay, this is a bit of a weird thing. First they say distance is defined to be the magnitude of the displacement, and then they say that it's not. It's important that the distance is not the magnitude of the So I think what they mean here is when they say distance traveled, that's what I tend to mean when I say distance. Distance traveled is not the same as the magnitude of the displacement. And the example here is that a cyclist rides 3 kilometers west, then turns around, does a U-turn and rides 2 kilometers east. Question A, what is their displacement? And question B, what distance do they ride? So the first thing they do is define plus x to be in the east direction and minus x to be in the west direction, which is fine. You can define that any way you want, but once you do that, then you know that the initial delta x is negative because you're going west, minus 3 kilometers, and then the second 2 kilometers to the east is plus 2 kilometers. So when you add the two displacements, you get negative 1 kilometer. So they end up 1 kilometer to the west of where they started. So that's the displacement. The question is, what's the distance? Well, the distance they traveled is actually 5 kilometers because first you rode 3 and then you rode 2. It doesn't matter what direction. If you had an odometer on your bike showing how far you went, it would be 5 kilometers. So the magnitude of the displacement is just the absolute value of negative 1, which is 1, but the distance traveled is 5. And then say section 2.2 is about vectors, scalars, and coordinate systems. This is about using this plus or minus to indicate direction in one dimension. So there's sort of a difference. We'll talk about this a lot more when we get into chapter 3, but we say that a scalar is a quantity that has like a magnitude, a size, but no direction. And that's typically what you type in a calculator. But I guess if you think of temperature, for example, or mass, these are scalar quantities. Even though temperature can actually go zero, go negative. There's a zero temperature on the Celsius scale anyways, and it allows you to go to negative. The negative doesn't tell you about direction there. It just tells you, again, about this temperature. So okay, and then a vector is something that has a direction, such as displacement, for example, is a vector. You're going east or you're going west. And so you need a coordinate system to give you whether plus or minus tells you one direction or another. That's what that's all about. Sometimes we go to the right is plus, to the minus, to the left is minus, up is often plus, down is often minus. But you can define these any way you want in order to solve the problem you've got. Section 2.3 is called time, velocity, and speed. Basic idea, time it's a scalar quantity which increases with time. I don't know, it's just the reading on, for example, a watch or a stopwatch or something, and we measure it in seconds. So an elapsed time, I guess, is the difference between the final time and the initial time. So you could say that something takes, I guess if a lecture starts at 11 a.m. and ends at, actually if it starts at 11:10 a.m. like my lectures do and ends at noon, then the elapsed time's 50 minutes is your delta t there. So, okay. And then there's the whole velocity versus speed debacle. So the idea, and there's also average velocity versus instantaneous velocity. Okay, so let's go through these in the order of the book. Average velocity is defined as the displacement divided by the elapsed time. So it's delta x over delta t, or x final minus x initial, divided by t final minus t initial. So since displacement is a vector, it has a direction, the average velocity is also a vector. It has a direction as well. And there's some examples of that. If you go backwards minus 4 meters in the negative x direction, then and it takes you 5 seconds, then your average velocity is negative 0.8 meters per second. So the units here come from the units of the displacement divided by the units of time. So if you measure displacement meters, time in seconds, then you say that your average velocity is in meters per second. Okay, then there's something called instantaneous velocity. Instantaneous velocity is like, it is the average velocity, but only measured over a very, very, very small time interval. So you allow the time interval to get very short. So the denominator is a very small number. Also the numerator, the displacement, is a very small number. But when you divide those, there's a limit where it's your velocity at that moment, your instantaneous velocity. And that's also a vector because it has direction. But speed in physics means the magnitude of the velocity. So speed is always positive, and it just means without the direction how fast you're going. So if your velocity is negative 3 meters per second, your speed is 3 meters per second. If your velocity is 40 kilometers per hour, your speed is 40 kilometers per hour. Okay, you just take off a minus sign if there is one. And lastly, this chapter includes some graphs. So there's something called a position time graph. This is showing your position along perhaps the x-axis. You put that on the vertical axis, and then on the horizontal axis you put time, in this case in hours. And then it turns out that the slope of a position versus time graph down here, you take the slope of this, rise over run kind of thing, is equal to the velocity. Actually the instantaneous velocity. So all along here there's a constant slope. The rise is 3 kilometers. The run looks to be about 0.25 hours. So 3 divided by 0.25 I think equals plus 12. So there's a plus 12 kilometers per hour until suddenly the velocity changes at this moment, and then you've got the rise is now -3, and the run is again 0.25, so you get negative 12 kilometers per hour. So that's the velocity. You can make a graph of velocity versus time. Constant velocity of +12 switches to -12. And then if you want, you can take the absolute value of the velocity to get the speed. The speed is the same no matter which direction you're going in this particular case. You're going one way, flip it around, go the other way at the same speed. So you just see 12 the entire time. And that is all there is to today's reading. And when we get to next class, we'll start talking about acceleration.